So, in this particular video, we're going to focus on part 3, which is on migratory insertion, where we looked at this particular topic focusing on the skeletal equation. We have X, which cleaves from M and migrates to Y, and what happens as a result of this particular migration is the formation of this particular intermediate product, where we have our M actually bonding with our Y and Y bonding with X. So we have the insertion of our Y in the MX bond, looking at it skeletally. So this particular product that is intermediate is coordinatively unsaturated complex, and to achieve a saturated complex we introduce a ligand, which is L, and L, what it does is that it actually completes this saturation by bonding to the metal. So as a result, we actually have our L bonding with our M, and M bonding with our Y, and Y bonding with our X to form a coordinatively saturated complex. Now, bearing that in mind, for migratory insertion, we'll see another application of this in the creation of specific compounds, like for example a ketone. Now we have this particular complex which will undergo a carbonylation in the presence of a halide. Now this particular complex here we'll focus on is a catalyst called Tetracarbonyl ferrate, and this actually has an 18 electron count for the complex in total. However, this complex needs to become a good soft nucleophile, and to achieve that we actually reduce the metal center, which is what we have right there. Now looking at the first step, we actually notice that to accomplish that we use a metal which is sodium, or we use mercury. Now if we use two sodiums right here atoms, what happens is that sodium atoms donates electron each to the metal center, which is iron, and what that results in is the gaining of 2 electrons to make this metal here to have a charge of 2 minus. So what that results in is that the overall electron count of this particular complex now is 20 electron in this complex. Now this 20 electrons is too much, really too much. It actually makes this particular complex to be rightfully unstable. Now to make this complex to be stable, what do you think is going to happen? Yes, you got it. This particular ligand actually cleaves off, and what that result is the loss of a carbonyl and also the losing of 2 electrons that results in the formation of this particular complex with the overall charge of 2 minus. Now bearing this in mind, we have this complex that is created to be 18 electron complex first, and 2, this complex is known to be a good soft nucleophile. Why is that the case? The reason why is because if we look down, translating this particular complex over to this particular point right here, we see that this particular metal here has 2 negative charges right there, therefore making this metal to be I would say a sufficient nucleophile to actually perform an SN2 reaction when we introduce a halide. So once we introduce a halide, in this case we actually use R bonding to a bromide, or sometimes iodide, or any of the halogens, but we'll use bromide in here. Now what happens is that first the metal performs an SN2 reaction, picking up the R, and this R cleaves from this bromide, and this results in an SN2 reaction that leads to the bonding of our R group on the metal side. We'll call this R1 right there, and we notice as well that there is now just one negative charge right there on the ion. The ion is still a nucleophile and it performs a second SN2 reaction with another halide, and what results in this particular case is the ion picks up the second R2 and this actually cleaves off, and this results in the formation of our R2 right there, and in here we have our R1 positioned right there. Now this formation here of two R groups that are actually cis to each other will result in a migratory insertion focusing on the R1 here with respect to the carbonyl right there. So they are both cis to each other, and what happens is that there is usually an external carbonyl because it is in the solution, and what results in is that this particular ligand triggers the migratory insertion, where we actually have this moving over to this particular metal right there, and this R group actually migrates and inserts itself, and this results in the formation of a particular carbonyl right there, and what that results in is the formation of our first intermediate product right there, and that is what is formed in this particular second step. However, there is a problem with this particular first product that we created right there. The problem is that due to the high pressure created with this particular or by this particular carbonyl groups in the solution, we're not able to perform a second migratory insertion with respect to this R group right there, which is the R2. So in order for we to reduce that pressure, what we do is that we actually add a phosphine ligand to this particular solution that results in a ligand migration that is going to be shown in this next step. So phosphine, once phosphine here is introduced as a ligand to this particular part right here that we actually dove into here, instead of carbonyl to be involved in the triggering of the migratory insertion, we're going to have phosphine to do just that. So what happens as a result is phosphine comes in here, and this actually performs a migratory insertion in this particular carbonyl right there, and what that results in is the formation of this right there, R2, and at the top here we have our carbonyl attached to our R1 right there, and we have our phosphine that is actually right there. Now the next step is to actually trigger the R2 to actually perform a migratory insertion, and to do that sometimes you can use either the carbonyl as a ligand to come in to do that, or you can use phosphine, but I will just use carbonyl for now. And carbonyl comes in here, and what happens is that since phosphine is actually introduced already, what it does is that it triggers a poor leaving group to actually execute that particular migratory insertion, and what results in is we have this actually created in terms of the formation of a bond with the metal, and then this actually performs a second migratory insertion, and what happens is to accomplish that this pi bond becomes a lone pair, and the lone pair reforms the double bond right there, and then this particular bond cleaves right in this particular case, and we have our phosphine actually leaving the group as a result of that. So what happens here is that we actually create our product, which is a ketone, and we are able to recreate our tetracarbonyl ferrate dianion right there. So that's about it for this particular video. Hope you're able to understand the ligand migration that is happening right in here to favor the migratory insertion that leads to the formation of our ketone product when we use a tetracarbonyl ferrate dianion catalyst to trigger this particular carbonylation in this particular reaction. All the same, stay smart and believe in yourselves.